Hello, my name is Jason Koenig, and I'm here to discuss adaptive restarts for stochastic synthesis. Program synthesis is the problem of generating a program that satisfies a specification. For us, a specification is a set of input-output examples called test cases, and programs are acyclic data flow graphs where the operations closely model the x86 instructions. Stochastic synthesis is a particular technique for program synthesis where we start with some program and propose random changes called moves to generate new programs. For example, we might redirect an edge from one node to another, replace an operation, or introduce new nodes entirely. In order to guide the search towards a solution, we introduce a cost function, which is a way to compare the program's output to the reference from the test cases. When the cost is 0, the program is correct. For example, we can take the program's output and the reference from the test cases and compute the number of bits that differ between them and use that as the cost. We can define the stochastic synthesis algorithm as a loop that repeatedly proposes new random moves and accepts the new program that's generated if the cost is at most slightly larger than the current cost. We allow slight increases to prevent local minima. To investigate the behavior of stochastic synthesis, we can plot the cost over the course of a synthesis run. Here we can see that there are large drops that separate long flat regions where not much progress is made. If we plot a whole bunch of searches on top of each other, we see that these searches often cluster around the same costs, which suggests they're passing through the same parts of the program space. We can define a plateau as a region of the search where the cost doesn't vary much compared to the overall variance in the search. Because most of the search time is spent in plateaus, they have a strong effect on the overall distribution of search times. When we plot many of those search time distributions, we see that they often have heavy right tails. In particular, the longest runs can be orders of magnitude longer than the shortest ones. This suggests that we want to periodically restart the search in hopes of running one of these shorter searches. The classic way to do this is with loopy restarts, which use a particular recursively defined sequence to choose when to restart. Under the black box assumption, where the restarts don't depend on any of the state of the search, the loopy restarts are theoretically optimal. If we reorganize this sequence, we can see that it has a kind of binary tree structure. To generate our adaptive restart algorithm, we're going to relax this black box assumption. We're going to use this binary tree structure, and we're also going to run searches concurrently rather than sequentially. When we do this, the key insight of our algorithm is whenever we introduce new searches by introducing new leaves to the tree, we're going to first run those searches and then compare that search, the cost of that search, with the cost of the parent. If the cost is smaller, we're going to swap them. And then we're going to run more search time on whatever search ends up in this parent node. And then we're going to repeat this on all of the other subtrees by comparing with the parent node and doing all of this recursively. This process ensures that the lowest cost searches always propagate up towards the root of the tree, where we spend the most amount of time on each individual search. The adaptive restart algorithm is most effective when the cost is a good predictor of the time to finish. So for example, if we have a low cost state that also has a high probability of reaching the goal, adaptive restarts do well. And if we reverse this, then adaptive restarts will not do as well. We compared our adaptive restart algorithm against the naive algorithm that doesn't do restarts, as well as the classic loopy algorithm, on two different benchmarks, one from the Cygus competition and one that we obtained by scraping binary executables. Our results show that adaptive restarts are up to 10 times faster than the naive algorithm and 5 times than loopy, depending on the cost function and benchmark. We invite you to see our full talk and paper for other details, including a visualization of the structure of plateaus, details of our benchmark, investigation into beta, and our full experimental results. Thank you.